Hello, everyone, and welcome to this week's Crunch seminar. This week, we have both our speakers from Crunch Group, and both of them would be presenting our paper reviews. Our first speaker is Josep. He's a PhD student with background on physics and some experience in modeling microfluidic systems. Currently, he's working with phase field models to describe cell migrations in extracellular matrices. He's a visiting researcher at the Crunch Group, and he would be presenting to us on the paper titled Physics-Informed Attention-Based Neural Networks for Solving Nonlinear Partial Differential Equations. You may want to start, Joseph. Thank you.
Thank you, Samdata. Yeah, so basically today I'm gonna comment this paper, which talks about the hyperbolic partial differential equations. And what it is with it, it's that previous papers weren't able to solve these hyperbolic PDEs when shocks were present in them. So this paper focuses on the neural network architecture in order to solve like rarefaction shocks or shock waves. So the motivation of this paper, the problem that they use as a benchmark to test this neural network architecture that they present is a problem based on the displacement of immiscible fluids. And basically, this is a problem that comes out when you think about of an oil reservoir in which the oil might come out because of the underpressure, but then as soon as the pressure underground goes below a certain point, the oil stops pouring out to the surface. And so one thing that you can do in there is like to inject water from one side, which is immiscible against oil, let's say. And then this water will push the oil to the surface by displacing it. So what we have here is a porous material, let's say the rocks or the sands, which is like embedded or it's surrounded by water and oil. And then by the injection of this water, we are able to displace the oil towards the surface. So this problem can be modeled by the Becquerel-Leverett equation, which is like also a theory, which takes like several conditions like laminar flow and different things. And so the thing is like they have this partial differential equation, which is a nonlinear advection equation. And the point with it is that the solution of this equation depends a lot on the fractional flow here. So this equation, it's basically describing the wetting phase saturation, U sub m, in terms of the fractional flow function. In terms of x and t. So basically what we have is that this fractional flow function is like, we have to think of it like, if you think of a given volume, then the fraction flow that will be of this phase saturation, let's say water, it will be depending on the saturation of that volume, of that element volume. And what this fractional flow function is saying is that it's only depending on the saturation of this phase. And by low saturations, we have zero fractional volume, which makes sense because if we don't have like water phase, there cannot be water phase flowing. And when we only have water phase, the whole flow, it's the flow of the water phase. So basically, when we think about this problem, what we want to know is at which position we will have the front of this interface of this phase saturation plane at a given time or at a given position. So we know when to switch technique or what to do to recover this oil. So when we want to know the position of this front, we also need to think of the derivative of this flow function, which, because if we do the chain rule here, we'll have the derivative of the flow function with respect to the saturation, and then the derivative of the saturation with respect to x. So if we look at the problem from the physical point of view, we can say that, so basically what we want to know is the position of this saturation plane. And the position of this saturation plane will be related to the change of water in the different volumes, right? So by doing some like developments, we arrive to the equation that tells us that the saturation plane like depends directly on the derivative of this flow flux. fractional flow. And when we plot this in terms of the saturation plane, because the derivative is symmetric, we have that for different saturations, like let's say 0.2 and 0.8, we have a similar velocity or the same velocity. So the result or the solution in terms of the distance, it's multi-valued. And this cannot be when we are talking about saturation, because in a given volume, the saturation should be unique. So in here, what it actually happens is that the saturation, which has higher speed than lower saturations, would overcome these volumes and producing a shock wave. So when looking at the problem from a more mathematical point of view, what we see is that this PDE is a nonlinear advection PDE. And for nonlinear advection PDEs, we have we know that the solution evolves as the characteristics of the PDE. But because it's nonlinear, these characteristics depend on the value of U. So when these characteristics touch each other, like from one side, like they are converging, we have a shock wave. And when they are diverging from each other, we have a rarefaction, which gives like different parts of the solution. So basically, to solve the shock wave, if we want to do it like by hand, let's say, because they are solving the same equation, what we do is like we just get the same area from like the advanced fluid to fill the lower saturated regions. So with this, what the article proposes is like, so previous results showed that pins itself were not able to address this shockwave problem. And what they tried to do is that based on the universal approximation theorem that says that you should be able to find a neural network able to approximate any continuous function, they want to find the solution for this problem. So to find this solution, this neural network, you have two different points of view. Let's say you can either change the optimization process or change the loss function. So in one of the related works that I'm going to present, what they did was they focused on the loss function and they added dissipative terms, which is something that you usually do in the traditional schemes in order to be able to solve the shocks. But in the paper that I'll be presenting today, they didn't want to modify the loss function and they just worked on the architecture of the neural network. So in this work, the authors, what they basically did, they saw that the pin, given like location points and boundary conditions, was not able to fit the shock wave. But when they included the diffusion terms, the pin would actually learn this equation. So they tried it with different fractional flow functions with concave, non-convex, and convex functions. And what they saw is that they could model or fit the rarefactive wave, but not the shock wave itself. So this was the result. These were the results without the diffusion term. And then when they introduced the diffusion term in the PDE, they were able to actually model it. So the challenge they are proposing here is that they want to solve the same problem, but without changing this PDE. Another related work that is very important for this paper.
Josep, can we see the diffusion term? Can you see do you have the details of the diffusion term?
Yeah, so basically what is happening is that the PDE itself has like a chaotic loss function because
I'm just trying to see what is the epsilon values is. They do it by hand, right? They don't automate. They don't find. Okay.
Yes. And basically what they saw is that this diffusion term was smoothing the loss function distribution.
Yeah,
so
that's standard. You have a very viscous solution. There's something called spectral vanishing viscosity, which would work very well here. But I know Hamdi Chalepi, he's the chair of the Stanford University. I would, yes, spectral vanishing viscosity would work really well. Or some entropy condition or something else to make it unique. But yeah. Okay, thanks.
Yeah, so basically another important work that they reference to is this neural machine translation by jointly learning to align and translate. And in this paper, basically what they are doing is like they are simply translating sentences through a bidirectional recurrent neural network. And what they do is they introduce an attention mechanism that would learn, like the attention mechanism is for a feed-forward neural network, a single layer. And what it does, it learns the relation between the hidden states and the previous hidden state of the following cell. So in this way, they are able to introduce a parameter or context vector, which will tell how important is the actual situation or the actual hidden state for the current word that they are trying to predict. And so in this paper that I'm going to present today, the PN neural network for solving nonlinear partial differential equations, they proposed an architecture based on GRUs and the attention mechanism. And they are trying to approximate these sharp shocks without the necessity of like changing the residual or like introducing where the shock wave is going through. So basically what they do is they set a discrete version of the domain of for the solution for the saturation values of one of the phases, let's say water. And then because they have discrete values on X, what they do, they reproduce or they represent their solution in terms of as a vector. So for each value in X, they'll have a corresponding solution of the saturation value. And the inputs of their architecture, it's time and M, where M is the relative mobility between the two immiscible phases. So this is basically the main architecture they are using. So it's based on like a feed-forward network to generate the first hidden state, and then a set of GRUs and another set of GRUs with an attention mechanism connecting them to. So what it is important to point out from this method or from this architecture is that they impose both the boundary conditions and the initial conditions by they just concatenate the boundary conditions and they simply impose the initial conditions into the architecture. They do not allow or they do not incorporate those in the loss function of the neural network. And by doing so, they are able to get the results that they get without using any examples of the solution. Again, also to get the solution of U, of the saturation values, they apply a sigmoid activation function because they want the solution to be in the range of 0 and 1. So their loss function is basically made from two terms, and this is basically the PDE. And what they do here, they use a finite discrete method, like the central difference method, because they have X discretized. They have X discretized basically. Even though R1 could be computed because they know the functional form of R1, this one could be computed in terms of the automatic differentiation. But they just commented on the paper and they do not actually say if they have tried it, tested, or what are the difference of these results. So yeah, I have no more comments on that. Yeah, another thing is that the loss function is made on the Frobenius norm, which is basically the Euclidean norm, but for vectors. And for matrices, and what you do is just concatenate them in a 1D vector. And the good thing about this norm is that it is differentiable, so you can use backpropagation with this loss function. So to make sure everyone knows a bit about the architecture, I want to introduce a bit the gated recurrent units. And these units, basically, they receive an input and a hidden state on the previous time, and they output another hidden state of the current time. So basically, we have two different gates, the reset gate and the update gate. And if for me, it's easier when looking at the equations. So if we look at the update gate, we basically have that when the update gate is close to 1, the new hidden state, it's basically the previous hidden state, and it doesn't care about the current inputs of this time step. But when the update term is 0, update gate term is 0, it doesn't care about the previous hidden state, and it only considers the current proposed or current candidate hidden state, in which the current candidate of the hidden state is related to the reset gate in which we have introduced the previous hidden state. So I don't know if this was clear, but basically we have here a recurrent mechanism, which takes the previous hidden state and the input, and then it performs an activation function in which it takes into consideration the updates gate in order to get the new hidden state that will go through the next cell and everything. So in this pin architecture, what they did, they just input the T and M values. And this, they allowed them to generate the first hidden state, which would go through all the way, like all the GRU units. And then from the GRU units, they would create the latent space of first hidden states, let's say Y. And these hidden states would come into the attention mechanism that would produce in the same time the context vector, which is, again, concatenated with the previous solution. So in here, what they are basically doing is like they are taking advantage of the correlation of all points, like all the context and the correlation with the previous solution in order to get the new solution. So to go a bit deeper on the attention mechanism, basically here what is happening is that they introduced a fully connected layer that would learn the relation between these first hidden states and the hidden state of the following layer of GRUs, let's say. So they normalize it by rows. So they normalize, so for each, what's happening here is that for a given time or for a given point, what they do is they correlate the context of all the system in the same point, and they give it a certain weight, which will relate like how much each hidden state of the first layer is important to predict the solution of the current time. And so with this, what they get, well, this was a general thing, like basically you input T and M, you generate the hidden states, you correlate them with the previous solution, and then you get the final solution through the GRUs layers.
Excuse me, quick question.
Yeah.
What can you remind me what is D0 and D1 in general? D to the I minus 1.
Yeah, so H0 is the output of feeding the single layer neural network with T and M, and then D0, this sorry, I didn't mention it. It's basically what they do, they impose it to be the same as HN, YN, sorry. And sorry. D0 is HN. So in this way, what they were saying is that they would keep the information or the memory of the previous GRU layer. Does it make sense?
I don't see why they have to do that extra in addition to using C, but they must have a reason.
Yeah, the unique motivation that they did for using D0 as HN was they were just saying, I think basically they needed to have a first value, a first hidden value. So they just say that, okay, why not just put this one?
Okay, because it looks a little bit arbitrary just to take HN, in the sense, why not take some other H which corresponds to the middle of the domain, right?
Yeah, I guess it's because HN, I mean, this is not gonna make much sense, but I think one of the reasons it's because HN has gone through all the layers, and so in some way it could have some information of the whole system, but this doesn't make sense because the purpose for this is C squared, which
yes,
is actually
exactly, is to take account of all the individual points, right, through the alphas. Okay, thank you.
So yeah, I think it just they just needed to have like an initial value. So
okay, thank you.
So yeah, moving forward, I'm gonna
sorry, I have a question. Hi, this is Leonard from Crunch Group. I'm just wondering, so Do you, by any chance, know why they used GRU cells with the attention weights instead of, for example, like a transformer-based architecture, which is sort of the more recent attention-based sequence model that has been shown to be like much more parallelizable and better than recurrent cells?
Actually, I don't know, but I'm guessing it's because GRUs are simple units, like they do not have many parameters in it. And by using this attention mechanism, what they are doing basically is they're introducing the information of each single point in the system at a given time to get the solution. So in some way, they are getting to get the solution, and at X sub I, they're using the information for all the systems. So I think GRU units are only because of their simplicity, and the same would apply to the tension weights. But I don't think they gave it much a thought, because this architecture, it's basically the same architecture that it was used in this paper. So they just applied it thinking of, okay, if in here they are using the context vector, because in here, basically, when they are translating, what they are doing, it's like they are taking into account previous words and like the following words from the one that they are trying to predict, right? So I think it's the feeling is the same. So basically what they are trying to simulate, to reproduce here, is like, if I'm trying to represent the shock, I should take into account the solution previous to the shock, which is the information at different X, and the solution next to this shock. And yeah, I just think they just didn't give much of a thought about changing the architecture.
Oh, okay, yeah, that makes sense. Just yeah, it was just on my mind because like in most sequence modeling research nowadays, the transformer is kind of the de facto attention mechanism.
Yeah, and the multi-headed, yeah.
Yeah.
Maybe I can add a comment here. For the GRUs, because they have the bidirectional capability, maybe it's better for capturing the shock rather than the other transformers.
Yeah.
Just
That could mean, Okay.
Right, thank you.
Thank you, Hassan. So going to the results, because in their loss function, they are only optimizing it for the PDE, and they do not introduce the initial conditions or the boundary conditions. They actually get a fast optimization of the model in terms of the loss function very quick. And I mean, this is good because with only 200 epochs, they are able to actually solve this problem. So the results, they went, so in here, I'm showing some of the results.
Excuse me, Lulu from Japan. I didn't quite get, how do they do the time evolution?
The time evolution?
Yes.
So basically, the time is the input into it. So they discretize, so you can put any time that you want. And basically what you have is in your PDE, you have the time evolution included in it. So I do not see now. I do not. But basically, so the time of so you introduce the time that you want, okay, and then you have the previous solutions already. So, and the thing is that you have all the domain discretized. So at each time that you input into the equation or into the model, you are solving the solution for all points in the domain at once.
Yeah, basically the solution at different time snapshots, they are coupled through the loss function, but not coupled in the architecture.
Not coupling the?
Not coupling in the architecture. So in the architecture, there's no information over the previous time when you try to predict next time.
Yes.
Okay, I see. Okay.
Yes. So basically, what's happening here, I think this question will be answered with the attention weights that I'm going to provide you later. But yeah, basically they have this fast conversions. And these are some of the results for the training they did. By rows, we have the M's, different mobility, relative mobility values. And in the columns, we have the different time steps. So what they see is that they are able to fit, I mean, we have 3 different regions, right? The rarefactive wave, the shock wave, and the unaltered solution. They are able to fit properly the first region and the third region, rarefactive wave and unaltered solution, but they have some problems in the shock wave. And the problems that they have, it's like they basically have a smooth shock wave. And this resembles a lot like to the traditional schemes that when try to solve them, because here they have kind of an oscillation going up and then down. So yeah, this is basically the solutions that they were getting for different M's. And and they tried to, and they also plot the attention mechanism with each of the solutions. And what they saw is that this attention mechanism at each time step was able to figure out the prediction, the location of the shock, giving to the architecture the flexibility to adapt its behavior to the shock. So basically what's happening is that because the attention mechanism, it's gathering the information of all the latent states in the domain, it is able to compute or to identify the shock location. And what they see is that just behind after the shock, the attention mechanisms give a constant value to all. I mean, alpha is constant for all latent variables, all the hidden variables. And then they have the transition, and they also have, and following, they have the whatever it is, the solution of that single forward neural network. And yeah, basically what they have is that this attention mechanism is able to identify the shock, the discontinuity, and allow the neural network to change its behavior accordingly, so they can have the proper solution for it.
Joseph,
So,
I have a question. Sorry,
yeah.
This is Assam from Brown. So do you know if the X coordinate that they have, it's a fixed coordinate that they use?
Yes. So basically they fixed all X coordinates, they discretized it beforehand, and the unique continuous variables are T and M.
And does that, and they use the finite difference in the loss function. So
Yes.
then the architecture here depends on how fine they want to define the X coordinate, and then how accurate they carry out this finite difference in the loss function. So it means that if they want to have a very fine resolution in X, the architecture is the network is going to be very big. So many units that they have to use, correct?
Yes, but this is also a result they show at the end. But yes, you're right, because they discretize X, they have to use finite difference in the loss function. And this would make you think of like what you were just saying, like if I want to have a fine resolution, I should discretize further, right? So the last result they show in the paper, they show that this is not quite so true. I mean, the resolution, it's not highly dependent on the discretization, but it is at some rate. I'll show this result at the end of the slides.
Thanks.
Joseph, it's Amir from Brown.
Yep.
I have one question. Can you go back to the discretization?
Yeah, wait. Yeah, I don't know which one you want. Yeah.
No, yeah, this one. So if you see R2, so basically they are using the central difference for flux discretization, right?
Yes.
But still they're able to solve this hyperbolic PD, which has a preferred direction of information propagation.
Yes.
So how they're stabilizing the...
It's an unstable. Abega is right. That's an unstable scheme.
Yeah, that's the whole point of the attention mechanism. So actually the comparison they do at the end, that as I was commenting to San, they do the comparison between the central scheme and the upwind scheme, which is stable. And that's the whole point of the attention mechanism. So it's the attention mechanism which gives them the capability of stabilizing the solution. Or at least this is what I understood. I mean,
Okay. Thank you.
No, but I just confused. So, but attention is basically you are doing the sequence to sequence. The attention is nothing else inside the sequence to sequence architecture. But the find difference is for the output. Right?
Yeah. So
It
you're
has
saying
nothing to do with what happened inside.
Yeah, you're saying basically that the solution could blow up even if you are, I mean, even whatever you're introducing inside the finite difference. But
Yeah, there are different things, right?
yeah, but I think that this thing that you're commenting, Lulu, is the same reason why they are having this small oscillation here. So, and this is what the finite difference, it's related to the, I mean, this PN network, it's related to the traditional schemes. I mean, yeah, I don't really know or understand why it converges. I mean, I would just say that the loss converges and the neural network makes it for it. But
yes.
Excuse me, quick question about these results. When they write time step in the legend, do they actually mean time or different value of the time step?
Again, so
because it looks like time actually, because the shock is moving to the right.
Yeah, no, so sorry. This is like time step 0.04, time step 0.2, and time step 0.
Right. Is this the time or the step size of the discretization?
This is the time.
This is the time. Okay.
Because,
so the shock is moving to the right and they're showing 3 snapshots, right?
Yes. Because the time here, they don't discretize time. Time and M for them are continuous, because they only feed the value into the first single neural network.
Right, but they discretize it for the loss function, right?
Yes.
Yeah.
So yes, but in the loss function, I mean, they could introduce any time, right? Because it's just the collocation point. So.
Right, but that's why I was asking what is in the figures. Okay, all right, thank you.
Josep, the interesting thing is that this is not that they don't show any oscillations. These are smearing, which what you point out is actually just dissipation. So what creates this dissipation? That's the question here.
George, I sent you a message. It's like almost like a neural network approximation which uses a fractional derivative, right? Because of the non-local character that they use everything in the domain.
Oh, you mean in time?
In space, a fractional derivative in space.
Oh, because they have a GRE.
Yeah, the alphas can be thought as weights of how much you take into account all the points in space. So that's what is giving them this stabilizing effect, because they use information from the whole domain.
Yes.
But it's happening in the latent space, not in the physical space.
It's happening in the latent space, but y1, y2, yn minus 1, and yn all have informations about the specific point in space. So the y1 and y2, etc., is just the latent space for the corresponding points x1, x2, etc. So that's what the attention does. It couples all the points in the solution through these alphas.
See.
Okay.
But Panos, it is still not clear how they are stabilizing this.
I agree. Because when I saw the central scheme, I thought, okay, this is the recipe for disaster, right? Yeah.
But Panos, you may be right, because the second order difference will give you some dissipation, right? But then if it's like a fractional derivative, and you think you can have both odd and even derivatives, and that could
Yeah, so they said that they don't want to do it with an explicit term, but I think that what they are doing through this attention mechanism is that they're introducing an effective dissipation, but not the simple, second order dissipation, but something more non-local. That's why I thought of a fractional derivative, like a fractional dissipation term.
Yes.
But still, it's a mystery why it stabilizes the central difference scheme. And also, I don't know, I mean, like the other question that was asked, how many discretization points will you actually need?
Yeah. I mean, that's okay. Just let me get there, and I think we will have a further discussion in it. So, yeah, just moving forward. Basically, they were able to interpolate between the range of M. Like they were training for M from 2 to 100 in in a step of 2, and they got these two different solutions for 4.5 and 71, which are both outside of the training set. And again, they were able to get the result properly, let's say. I mean, it was a good fitting, even though it smoothed the shock. It was able to locate it properly and to adapt the pin solution to it. They also tried it for extrapolating for values of M outside the training set, and they actually tried for M equal to 140, 250, and 500, and they saw that the further they get from the training set, their solution would get worse and worse. So yeah, they also said that they would recommend for retraining the neural network or the model for this, and which actually makes sense because here they completely missed the rarefactive way, and here this is a shock, but it's so smooth that it kind of looks like the rarefactive. So and here it's everything you were talking about and discussing. So here what they tried was like they changed the discretization of the X values to see how the residual error would change. And again, what they saw is that the residual error was like lowering as they increased the resolution of their discretization, but it wasn't highly dependent. So there's the significance of the resolution, it's not that high, but they do not provide an upper bound for it, right? So they do not say like, if you put discretization on X to the power of -1, we don't have an upper bound of the residual error to say until which point you should discretize your measure, your system. And yeah.
So a quick comment here, Joseph. I think it would be also interesting to see when they decrease one order of magnitude delta X, so they increase the resolution. So the GRU units are 10 times bigger, and how the computational cost would increase in this case. They have way more parameters to optimize. So that's I think, I don't know if they talk anything about the computational cost of that.
No, they actually, that's one thing I was thinking about, because training GRUs, even they are simpler, I mean, it has a computational cost. But the thing is, like here they decreased, I mean, they refined the mesh for like a power of 10, as you were saying. And the residual error just went down for 0.13 to a power of, So they actually, by reducing the GRU unit for a factor of 10, they don't even get that much improvement on the residual error.
So there is also a pessimistic way of looking at it, that it's actually not converging, right?
Yes.
That as you refine the resolution, maybe at some point the central scheme will come back and bite you.
No, I don't think so. I think here what they see is the floor or ceiling of the optimization error. around that 10 to the minus 5.
Yeah, they cannot improve this solution by refining the mesh further. Yeah. But for this, they also tried to change the scheme. Like they actually did, I mean, they had the central finite scheme and the upweight finite difference scheme. And what they saw is that the solution that they were providing, obviously the upweight finite difference scheme was getting a closer solution to the shockwave, probably because of this inherently diffusive effect that it has this scheme. But the argument that they were giving is that having these both solutions converging this good or this well to the analytical solution makes them think that this neural network architecture does not depend on diffusive terms to converge. And I think that closes the question you were, I mean, I still do not understand why there is converging. I mean, the only thing I can think of is on the attention weights. But yeah, basically the fact is that the architecture is converging and converging pretty good to the shock. So the conclusions and a bit of discussion of this paper is that PIANS offers a good convergence and kind of a fast learning rate for the hyperbolic PDEs when shocks are present. And their solutions represent a smooth shock, so they are not able to represent this sharp shock, let's say. And and it's because of the attention mechanism they are able to locate the shock and allow this PIAN architecture to adapt its behavior to properly resolve this solution, right? And so this PIAN architecture is also able to interpolate and extrapolate close to the training. And the PIAN resolution, it's not highly dependent on the time steps or discretization of the system to capture the shock. Again, probably because this is because of the attention mechanism, which is taking the whole discretization or the whole domain to see where the shock it's occurring, it's located. So from my point of view, I think that PIAN seems a reasonable option for solving the hyperbolic PDEs, even though because of its discretization scheme, I'm not sure if they would, I'm not sure how good they will perform in 3D domain, because even though if you do not have to fine mesh your grid that much, it's still a lot of points to compute. So yeah, I don't know how well would it scale to different dimensions, but the truth is it's able to converge and to approximate the solution for hyperbolic PDEs with shockwaves. The GRU is able to extract the relevant information exploiting the correlations between following points or like neighboring points, and the attention mechanism is able to provide the location of the shock and giving this elasticity or this flexibility to the neural network. Again, it's important to point out that they were able to converge or to resolve this problem without using real data, without using data, only with the initial conditions and boundary conditions. And moreover, so this is the system I'm currently working on. And in my system, this is a Canhillier equation. I have a very high or very steep gradients in which I'm trying to model cells migrating through this porous material, which is an extracellular matrix. And I think this same attention mechanism that was able to identify the shock location would be useful for my system, because in a sense, it would be able to detect where these high gradients would be. So the problem I'm having with pins is that, again, it's not converging the solution. The solution, it's not converging, probably due to the high gradients I have here. And I think this attention mechanism could help me, and like many other problems, related problems where we have steep gradients, to locate where these gradients are and to allow for the pin to adapt the behavior to it. So thank you very much. And this is all. So if you have any questions, feel free to ask.
Yes, I have another. Sorry, I have another question. If you go to the plot of the architecture of the network, Yes. So for network here, as we can see, during the training, the x1, x2 to xn always the same, which means we have a network. And when we train the network, we always have the same input, which makes me thinking whether this is really useful or not. Oh, I mean, whether this GRU in the bottom is useful, GRU on the top is useful, definitely, this sequence output.
I think the fact here is related that from this X, you get the context vector, but this context vector is also concatenated with the previous solution. So
yes, I know. So basically, my question is, so this part, whether this part of GRU makes sense or not. Because you have some network, let's say this is a black box. For this black box, during the entire training, the input is always the same number constant. Right? Which means this is a constant.
It's a position in the domain, right?
Yeah, but it's fixed. It's a constant, right?
Yes.
You never really care. So it's really, you are outputting a constant.
But really the hidden state, H0 would be different because you have different time.
Yes, yeah, that's right. This only thing that makes sense is actually 0. But then it's whether we really need a GRU.
And what would you suggest in terms of like introducing a hidden state that would represent? Because the whole point in here is that for each position in your domain, you have a hidden state which kind of have information of its neighbors, and then you have the attention mechanism, which is taking into account all these correlations, right?
So basically so for Y1, Y2, until Ym, they are only functions of H0. They are not really functions of X1, X2, because X1, X2, they are always constant.
Yes.
One thing, Lulu, here, I think because the GRUs are bidirectional, so Yn can be a different function of all the points that you have. So even though the input to the GRU, the encoder is the same from the X, but when the gate parameters are changing, so the hidden, the latent space Y can be a different function of the points X. It's going to have a different non-local effects because of the bidirectionality of GRUs, I think. But what is not very clear here is not the final solution is not a continuous function of X, which I don't think it's going to be useful.
Hi, this is Thomas from MTSU. Hi, Josep, what do you think is the new thing that this architecture brings to the table? Is it that is the attention weights are 7 as a smoothing mechanism?
Yes, I think it's definitely the attention mechanism applied to the problem. So
okay.
Yeah, because as they were saying, like GRU, it's like a black box that in some way it's it's using the information it has, but it has on both sides, on both sides, yeah. But the proper correlation, or what is important here, is the attention weights.
Okay. Thank you.
And because the thing in here is like, because you are solving this on the same time, like you are having the whole solution, the discretized solution, solved for all points, like in the same feed forward, right? So yeah, I think it's just the fact that through the attention weights, they are able to introduce the correlations of all points to the solution, which they compute at all points again.
Okay. Thank you.
I think Professor Matthias has questions.
Yes. So first, thank you for this nice talk. I must admit that I really did not fully understand this attention mechanism. Let me just drop my hand. I wanted to comment on these oscillations, which are called overshoots, or this smearing out of the shocks. So this, first of all, I'm not talking about stability. I think there were some remarks on this central differencing. Of course, there are some stability problem, but if you think about, or if you talk about qualitative behavior of solutions, what we have here, then there's a good tool which is also well described in the book of Levesque, namely this modified equations approach. And it is well known that it depends on the order of the discretization of the scheme, of the spatial order. So if you use a first order scheme, then this results in smearing out of shocks, like a Lax-Friedrich scheme. And if you use the second order scheme like here, you get these overshoots, these oscillations. And so from my point of view, these oscillations are natural. They come from the discretization. What is somehow surprising is the smearing out of the shocks. And somehow I would guess that this is an effect of this attention mechanism. But I mean, this would be a guess, but it's not from the discretization. So this smearing out comes from a first order discretization, like this upwind discretization. Yeah. So for the upwind discretization, I guess we don't see any oscillations. Yeah. So this would be interesting to look at. But so the tool to look at is this modified equations approach. But of course, this approach is without this neural network part. So I just wanted to comment on this.
Yeah.
That some part is somehow expectable, and some part is somehow surprising.
But yes, I think, I mean, also the book of Oliger and all these people, that's what I think what they are doing is they start just like the Lax schemes. They start with a central scheme and then they use these modifications. But instead of the known modifications, they use a neural network. But the question is if this architecture is the best.
Yeah, I mean,
to achieve this type of effects.
Yes, there are some theorems that tells you that if you want to get higher order schemes, you must use nonlinear schemes, even for linear problems. And
yes,
so this is somehow the story of this flux limiter and so on, of these schemes. And here, of course, neural networks are also some nonlinear methods. So it's also maybe a way out of to create higher order schemes, maybe.
Yes.
Hi, can I ask you a question? I'm Ting Wei from Brown. So I want to ask a general question about the problem setup. Can you go back to the PDE? Yeah. Okay, the PDE. Okay, thank you.
I don't know. Yeah.
Okay. Okay. So actually, it seems to me that this PDE is related to the Hamilton-Jacobi equation. So if you take the integration with respect to x, then the integration of u with respect to x will be, I think, if I'm not wrong, then this integration will be the solution to an HJ PDE where the Hamiltonian is given by the function f. So actually, I don't know. Maybe this is a new. I don't know if we think about a couple of equivalent problems, and then we can have neural networks designed for each problem. Then maybe different neural networks, the different problem will benefit from different neural network setup. Then for different problem, we may have different neural network methods, and then combining those benefits from different neural networks, the solution may become better. I don't know if I'm too vague, because if you think about the solution U, then you have this shock. Then it may be hard to use a neural network to approximate the shock because it's not, the derivative is very high. But if you think about the integration, that means you don't have the discontinuity, you have the non-differentiability. So you may have a convex function which is non-differentiable. Then maybe under this setup, the neural network may be, more suitable. I don't know. The attention mechanics may be applied to that setup, and the performance may be different. But I'm not sure. I don't have experience on that, but I just want to mention this point and see what do you think?
Yeah, actually, I do not have experience in that either, but yeah, basically what you're saying is like trying to solve the integral form instead of the differentiable form, right?
No. When you do the integration, it's still a differential form. It's still a differential equation, a PDE, but it's different PDE. It's like the derivative dv dt equals f at dv dx. So it's different.
Okay, yeah, no, I mean.
Yeah,
no.
well, okay. Just some comments. Okay, thank you.
Yes, Professor Matthias.
Yeah, I forgot there's another big problem in this topic. I think George, he touched it slightly. Namely, here in these hyperbolic nonlinear problems, you have non-uniqueness of solutions. Yeah, so you have unphysical solutions, and somehow, of course, you only want to compute the physical one. And so one method would be these vanishing viscosity methods. Or I mean, this is a method to define the right solutions, or also, I mean, to define methods that are checking the entropy and something like this. But this is a really serious problem. Yeah. So you have different solutions, and some of them are unphysical, and you have somehow to tell the neural network what is the right solution.
Yeah.
Yeah, I may actually, and the people at, I don't know if not Trask is listening, but they try to introduce entropy constraints in 1D. They found some difference. This could be a good problem, because I think that the problems we looked at, Ameya was a SOD problem or lax problem, I think, and it didn't make a huge difference in making a little difference, the entropy condition. Ameya, can you speak about it? Ameya went for lunch. Anyway, I think that's a good discussion on this problem. So there's lots of interest. It's
So I think my first change would be to use a different scheme. I mean, we can also use a nonlinear difference scheme. Why not? It's not much more expensive, and there are some schemes that have a discrete entropy
condition. Yeah.
Mm-hmm.
Yep.
Do we have more questions for Joseph?
Joseph, you did a good job. We'll assign you more presentations. That's what you get when you're good. More work.
Thank you, Joseph.
Okay. Thank you, everyone.
So we'll move to our second speaker. Our second speaker is Zongren, and he would be presenting to us a paper review on the topic titled Neural Stochastic Partial Differential Equations, which are resolution-invariant learning for continuous spatiotemporal dynamics.
Okay, can you use my screen?
Yes, I can. Can you go to the slide presenting mode?
Oh, I'm sorry.
It works.
Yeah. How about now? Does it work?
Yes, it works. Perfect.
Okay, so we're going to study this paper in this talk. So the main contribution of this neural stochastic partial differential equation is it proposed a model. They name it neural SPDEs that extend the neural cities, I'll explain later, and neural operators to more to the stochastic partial differential equation problem. And this model, this neural SPD, learn solution operators of the equations in the form of like this U0 is the initial condition. This Kasei is a driven noise. It's noise. It could be spatial temporal dependent noise. Could be Gaussian. Could be anything. It's a randomness, and then the output of this model is solution.
Hello, Zongren. What is neuron CD? Do you mean OD?
No, neural CD. I'll explain this later.
Okay,
yes.
Okay, thank you.
Yeah. So and then like it learns the operator from observations, and such that those models are capable of processing incoming sequential information, unstructured or irregular sequential information, arriving at any arbitrary spatial resolution or temporal resolution. So before I move to this paper, I want to spend some time to talk about this neural differential equations or neural DEs community. So there have been many recent many works in this from this community in the past few years. So it all started with this neural ODE, the neural ordinary differential equation paper in 2018, and this good paper is has a lot of citations, and it's pretty. The idea is quite interesting, and followed by some other papers as extension to the neural ODE, like neural control differential equation, neural cities in 2020, and neural RAP differential equations. So you see there are a lot of neural DEs models from this community, and the last one is in this neural SPDs I want to talk about in this talk. So I'm curious why there's no neural PDEs. People move directly to neural stochastic PDEs.
Actually, there is neuron PDE.
All right, okay, that makes sense. And so for the neural ODEs is the idea behind neural ODEs is very simple. It's very straightforward. And then it is simple to understand. It's simple to understand, easy to understand. So this how can in conventional deep learning setup, we do this skip connection technique for neural network, like residue, ResNet, like DenseNet. They do the skip connections among all the layers. So you can consider this F is the active function that takes the output of previous layer as input and parameterized by some parameters, and then the output of current layer, this layer, is the summation of those two. And this is in a discrete manner. So if we move to the continuous version of this, we have the ODE. And so there are many ways to parameterize the solution, the mapping we want to learn. So in this way, they parameterize ODE, and they assume that they think that the model is the output of the ODE, the solution to the ODE at some time is the output of the mapping. So on the right here, you can see that so the input is X, output is Y. So this L theta 2, L theta 1 are input output transformation layer, consider that like a transform layer, and then this ZT, this sub T is solution to this PDE. So and in this way they learn mapping from X to Y, and the loss function, the key component of this neural ODE is that how do we do backpropagation? How do we learn this? So this F is parameterized by some learnable, trainable variables. How do we learn this? How do we do stochastic gradient? How do we do this update on those unknown parameters, latent parameters? So this capital L is kind of it can be any differentiable loss function, and this ZT, I think it should be Y of T1. So already if we consider this output input transformation layer as linear layers or count identity functions, then it's the output of the model. So basically, yeah. So the solution, not solution, the output of this model is the solution to the ODE. So you can use any ODE solver to solve this ODE with this. They can be those or hyperparameters for the ODE solver, and there is a way to do backpropagation through the ODE solver. The backpropagation through the loss function is quite easy. It's differentiable. Could be cross entropy, could be MSE, mean square error, but the backpropagation through the ODE solver is complicated. There is a way to this algorithm for computing the gradients with respect to this one and the theta, the parameters, the trainable, learnable parameters. So you can check the NeuralDis paper for this algorithm. But like, nevertheless, there's a way to compute the gradients efficiently instead of doing backpropagation through the iterations in the ODE solver. So here are my comments. Yeah, I want to talk about it. For every input x, the output is obtained by solving ODE with the initial condition. So after the parameters, the theta, are learned, then we have this model. So giving any input x, we solve this. We will obtain y by solving this ODE. And the second is so this is the name of the model is neural ODEs, but it is rather a ODE method for deep learning tasks. For neural network, it's not the other way around. It's not deep learning method for solving ODEs. So that's something we need to keep in mind. And Neural Cities is also very, it's a good paper, it's a popular paper. It's an extension of Neural ODEs model for irregular sequential data. So it's Neural ODEs idea, still the output of the model is obtained by solving CD, solving a control differential equations, and with, they had a control over time. So here's a remark. So previously in here, this T is artificial. It's made. It's not. It does not have any meaning. But in Neural Cities, this T actually means something. It means time, unlike Neural ODE. So this is Neural ODE from the previous slide. And so for Neural Cities, given some older data, sequential data, it could be the number of observations could be changed. It could be changed. The locations, the collocation points for this observation could also be inconsistent among all the observations. So that's how we, that's what we call irregular or unstructured data. This is so for Neural ODE. The input is X. For Neural City, the input is sequential. It's sequential data. It's a sequence time series, for instance. So they deal with this. They incorporate the sequential data inside of the model, with the model by consider a control differential equation. So here the capital X is actually a process. It's a function. It's a process, and they managed to put this sequential as put them here, and that's how they incorporate sequential data with the ODE, with the model, with the differential equations. So the reason why they do this, because consider for Neural ODE for the inference stage, giving any initial observation. If the initial observation is the same, among all the time series, the output should be the same for Neural ODE, and that's clearly not what we want from for time series inference. And there's a theorem for kind of a universal approximation theorem for this CDE in the papers. And if we compare Neural ODEs with Neural CDEs, you can see that for Neural ODEs, this integration is done with respect to time, but in Neural CDE we have control. This is this X is a process, and output is you could consider this one as a matrix vector multiplication, and yeah. So they incorporate the sequential observations by interpolation, by some interpolation, make the process out of the observations. So now actually it's a control path, and there's some equivalence between neural cities and neural ODs. So if this axis they interpreted to be a continuous and differentiable process, so axis differentiable, and g theta is obtained in this way, and then the neural cities on the left is turned to a neural ODs with different parameterization for the right hand side of the ODEs. So here are my comments, and for neural cities, the output, which is a sequence in this case, yeah, it's still a solution to a control differential, to a differential equation, because but you know, we do not only care about the terminal value. We care about the whole process, the whole sequence, which is easy to obtain from the any ODE solver. And second, the difference between neural cities and neural ODEs is like the difference between recurrent neural network and fully connected neural network. So this model, it is a CDE, a control differential equation method for deep learning. Again, it's not the other way around. It's not the deep learning method for control differential equation. And you can consider this as a continuous version of RNN or GRU or LSTM. So this is the background of this neural SPD. So the neural SPD is, yes.
Zongren, can I ask you a question?
Yes.
For the control, so X is given by the data, right?
Yeah, yeah.
So it's not the control, or it's not the meaning of control in the optimal control problem.
No, I don't think so.
Okay, so there.
Yeah, it's controlled by the observation.
Okay, thank you.
And the motivation for neural SPDs are one, neural cities can only model temporal dynamics, but not dynamics varying both spatially and temporally. And B, the neural operators are able to learn this solution operator, but they failed to incorporate randomness into the system. I don't agree with this claim, but we can discuss it later. So the good news about neural SPDs is finally we have a model from the neural DEs community that cares about, you know, care about differential equations. So this is actually a model. It's different from the previous two. It's different from neural ODEs and neural cities. That is a model for solving stochastic partial differential equations. So it's not partial differential equation. Sorry, stochastic partial differential equations for deep learning tasks. It is for scientific computing tasks. Okay, so the stochastic. This is the type of the class of stochastic PDEs they deal with in the paper. This L is a differential operator. This side is linear differential operator, but I think they made this is a typo. It should be semi-linear differential operator. And then they did the experiments, the cases they do in the experiment section are all semi-linear stochastic partial differential equations. And the mild solution to this type of SPDs it's like this. So they further assume the differentiability of the Brownian motion, and they obtain the mild solution becomes in this format, and this H is expressed explicitly in this way. So the neural SPD, that's SPDs they consider. The neural SPDs are so that they make further assumption, and the mild solution becomes in this form. And the neural part, the parameterization part, is on the kernel function K and on the map H. So you can see that this H is parameterized by theta, and they do this by parameterize this F, capital F, and parameterize this capital G to obtain the parameterization of H. And here the U0x is the initial condition for the SPD, and this L, capital L theta is and pi theta, they are also input output transformation layer, or transformations.
Excuse me, quick question.
Yes.
So if they're given the PDE, the SPD, it means that they're given capital F and capital G. So why do they have to?
They assume that
parameterize?
they assume that the PD is unknown.
Oh, unknown. But they assume that it has this form. I see.
Yes, that's a very good point. I'll discuss this later. So I think that's one of the reasons why this model, the results are good for this.
I'm asking because you said that it's also a method for solving SPD. So I thought that the SPD is known.
Oh, yeah. I'm sorry. I don't think it's for learning the operator for SPD. It's not solving SPD. So there are not a lot of information of the PDE during the training.
But if you know the SPD, you can still use it, right? As a method to solve it.
I don't know. And then they have to propose a different method to parameterize this, because you know F, you know G, why parameterizing? So I don't think so. I think
as a more efficient way of solving it, I guess. I don't know.
Probably like physics informed neural SPDs, so like PD informed SPDs. Okay, all right. So this is whole schematic of this.
Sorry. Can I ask you another question?
Yes, of course.
So you have this formula for Z, T, and then you have the relation of Z, T, and UT. I don't know, U is the solution to the SPDE, right?
Yes.
So what is Z?
So this is a output transformation layer. So it could be identity function. It could be linear layer. So it's just a transformation. It's like the final layer of the regular conventional neural network that would do some linear transformation. I think it could be, it's not necessary, this pi theta, pi theta.
Yeah, the reason why I ask is from the mathematics you give on the top of this page, seems the formula for U is exactly in the same formula for Z. So I just wonder why we need this.
They may find that it's useful. It's a way of parameterization.
Yeah, sure. Okay, thank you.
No problem. It's like what they did in the neural OD, neural CDs, that they do this input-output transformation layer. They're not necessary for
Thanks.
No problem. So this is a whole schematic view of neural SPD. So this giving sequential data, input data, they somehow interpolate them into a continuous version, differentiable continuous control path, and the output is also, the solution to the SPD. So you can consider here, this is U0 is the initial condition, and we feed it to a input transformation layer and obtain Z0, and we put it into the SPD with parameterized kernel function, parameterized FH, and then we obtain the ZT, and then we feed it through the output transformation layer, and we obtain the final solution. So those two output transformation layers could be omitted. And this is question like asked, how do we do backward extrapolation, meaning that, so suppose that the initial condition is given here, how do we do backward? I think we can, the problem is it's not hard. We can do this backward integral, but they didn't explore this. I think it's pretty straightforward to do this forward extrapolation. Normal. There are two methods for to parameterize the kernel function. So here it's not just for parameterization for the kernel function; it's also for parameterization for F and G. So this two methods for parameterization of the model. The first one is by it's an ODE solver approach, similar to neural ODEs and neural CDEs. They obtain the ZT, the solution, or this one, the ZT, by solving a ODEs. So here, the this f is the Fourier transform. F is Fourier transform, and with this -1 is the inverse Fourier transform. So this ZT solution to the stochastic PDE could be also written in this way. And there's some lemmas that claim that with some assumptions on the kernel function, we have this. You call it, there exists a map A, the capital A is actually a function. So and they do this. This V sub t is obtained by solving this ODEs. So eventually, in the end, this Z sub t is obtained by this ODE solver. It's very similar to NeuroODE and NeuroCities. And I checked their codes on GitHub, and actually, this capital A is not function. It's not parameterized by a function. It's just a learnable matrix in practice. So here, this ODE, this A is just it's linear on VT. And another question to ask is, how do we do backpropagation? How do we compute the gradients with respect to this theta and perhaps Z0 through this ODE solver? Yeah, and similarly, they do this. They use this method, adjoint sensitivity method, to compute gradient through the ODE solver in a cheaper way. And yeah, another parameterization methods is fixed point approach. I didn't put all the materials, all the derivation here. If you're interested, you can check the paper. But if I put it this shortly, we obtain this Z sub t by solving this equation. And then the right hand side is expressed in this way. So here, the F is still the Fourier transform. This D means the Fourier transform on the spatial domain. And the 1, I think it's 1, it means this Fourier transform on the spatial domain. D plus 1 is the Fourier transform on the spatial temporal domain. And then this Z is obtained by some fixed point solver with Z0 and this one. So, and again, there's a cheaper way to do this backpropagation through this numerical fixed point solver. And the model, the neural SPDs, is space-time and resolution invariant because, so supposing like one observation is we have 3 fields, and the other observation is we have 4 fields. So the number of observations may be, the number of collocation points on the temporal domain may be different, but because they do interpolation first before they feed it to the neural network or to the model, so it is space and time resolution invariant in the input in this way for the input. And because the evaluation can be done for any XT, which means that the output is continuous. I think it's a differential. It's at least continuous with respect to X and T, unlike the paper in the first talk. So that is how they define this space-time resolution invariant. And yeah, and they did 3 experiments for 3. They solved 3 stochastic PDEs. The first one is this one, and for each SPD, they do 3 types of experiments. One is they learn a mapping, the learner operator from U0 to U. They assume that they don't have any observation on the noise cassette, and then they learn the mapping from cassette, this noise to run noise to U to the solution, assuming that of course the cassette is observed, but the initial condition is fixed. So yeah, and then finally it's a more general mapping from U0 and cassette to the solution, the initial condition and driven noise condition. So the target, the final target is giving an initial condition, giving observations, giving the driven noise, they learn an operator from those 2 to the solution, to the SPD. So this is a table, arrow table they provided, and they compared the neural SPDs with neural city, neural this rough differential equation. And I'm not sure how they incorporate this cities with FNO. And then they also compared it with DeepNet and FNO for different this capital N is number of I think it's total number of training observations for training, and it's weird that they solve the PDE SPD until 0.05 and time step size for time is 10 to the -3, so it means they solve it for 50 or 51 times. The ODE solver evolved for 51 or 50 times, and I wonder why they don't make it further. We care about the solution for later time for some cases.
Excuse me, quick question here.
Yes.
For the first case where they say that they don't know Xi, right?
Right.
What do they compare it to? How can they compare the accuracy if you say that the noise Xi is not observed? How do they implement it? I don't understand that.
What do you mean? So it's this side is for a sanity check. Then they know the error will be large because for the same user from the same initial condition, different driven noise yields different results, different solutions. So that cannot be the solution cannot be determined by the initial condition. That's right. So yeah. I don't understand your question.
Sorry.
I mean, what do they just specify Xi and run it?
Yeah, that's how they generate data, generate training data.
But they don't know what this Xi. I don't understand when they say we don't know what this Xi is. So they don't use any information about the specific path.
Yeah, they don't use the Xi for the training of their model.
Okay, just when they run it, but they use some noise Xi, the same noise Xi for when they run it and when they compare it to whatever is the solver that they have for the Ginzburg-Landau equation, right?
Yeah. Just they don't use any Xi to train their model. They
okay.
Yeah.
Okay. So okay, but during the training, they do need to train with certain paths of Xi, right? Because their formula depends on Xi.
You mean this one?
Yes, it depends on Xi t, right? You see on the formula, everything depends on Xi. So during training, they must have produced some other.
Yeah, Zongren, you didn't tell us what the data is.
Yes.
What data they use for each case? I think that's what we're missing.
For this one, the data is just the different initial conditions.
Right.
So it cannot be just initial condition.
It cannot be just initial condition because all their formulas depend explicitly on the path Xi t.
Oh no, I don't think so. I don't think so. I think they find a way to parameterize this.
Look, everything depends on Xi. So they must have trained using some paths Xi. I mean, otherwise, how do they do it?
Yeah, you make.
If you go to the previous slide, go to the previous slide, and not this one. You see the expression for capital H on the right-hand side. It has Xi t there, so you need to put some value there when you're training.
In the training, you probably they have all the trajectories. That's what the schematic shows. Look at your schematics. So input data, so they have snapshots all the time.
Yes.
So these are the data.
Right. So what they mean is that for when they evaluate it, they do not assume to have the Xi somehow, and that's what makes it mysterious for me.
I'll double check their codes. Their codes are I cannot run it on my computer, so there are some. Yeah. You make good point. I didn't consider that. Right. So they said this part is for sanity check, and I don't know how they did this. I didn't check the experience for the codes for this part. And okay, that's a good point. So I saw another question from. Do we have any more questions for this part besides this? So I understand, Panos, I understand your question. So in the parameterization of the model, we need.
This is Thomas from MTSU. Okay, I wanted to be sure if the design was implicit or explicit. Like, was it from the data or just 10% like we normally do, like in terms of the stochasticity?
You mean it's Kasei, right?
Yeah. Yes.
I think their model is explicit on, their model is this one, and they explicit put the stochastic part and the deterministic part here.
Okay. All right.
And it and the second experiment they did is for KDB equation, and they put it in. This time they solved it for a longer time, so they terminate. The OD solver terminates at 0.5 with a coarser time step. So and they do it. They tested for an even longer time interval to capital T equals to 1. And it seems to me that they in all the tables, they want to emphasize the functionality of the neural SPDs on this part, and they want to say that they're, compared to other neural operators, neural SPDs is better in accuracy for this part. And it seems to me that the arrow is significantly better than all the other models. But like, here are some comments and thoughts, my comments and thoughts. So like Panos pointed out, that compared to deep operators, neural SPDs make further assumption on the task. One, that the SPD is semi-linear. That's one thing. That's one assumption. The second assumption is the Brownian motion is differentiable. So this is the SPD, and although the PDE information is not known during the training, the relationship between the deterministic part and the stochastic part is hard encoded in this model. So in the whole parameterization of the model. So I think that's one reason why SPD perform better than all the other models. And like for instance, they don't know this they don't know this explicitly, the PDE, but they know that the F theta is learning this part, the G theta is learning 1. So I think there more information for, but neural operators don't have those information during training. And they claim that this is a screenshot from the paper saying that neural operator can model operation mapping the initial condition or the forcing and driving noise to the solution, but they have there's no way to learn from both of them. So this is kind of a where I don't disagree. So I don't know about FNO, but for DeepNet, learning a map from the initial condition U0 and the driving noise Kasei to the solution could be straightforwardly done by putting 2 branches, right? The one branch is for the initial condition, and second branch is for the driving noise. So this could be easily done for this type of problem, and I don't really understand why they put it cross here, saying that DeepNet and FNO are not capable of learning such mapping. So
maybe Lulu has done it with a Jin.
Yes, actually, you are totally right. So actually, DeepNet can be even more than this. So we have recently have worked on extension of DeepNet for multiple inputs. So let's say we have input of the U0 or input of Kasei. You can even have input of the boundary condition, the input of the forcing term. Can be anything.
Yes. So what I don't know why they said that neural operators cannot handle this type of problem.
Lulu has a new paper on what do you call
multi-input deep net.
Okay, Lulu, maybe you want to present it here.
Yes, I just put it in the chat. So basically in the paper, we further show theoretically, it's still universal approximation theory for the multiple inputs. Basically, you can assume it's extension of the chain theory from one input, one banana space to a product of banana spaces. Then we have formed a few experiments from initial condition to the initial condition, boundary condition to the solution, with initial condition forcing turn to the solution, with boundary condition forcing turn to the solution. Yeah, but you're totally right. Yeah, it's doable.
Yeah, it's so.
Lulu, have you applied to the stochastic PDEs?
Stochastic not, but I think it's at least theoretically it's doable.
Okay. Yeah. And that's it for the paper. I'll double check this. What the question panels proposed ask about this. How do we do the training? And for this way, if the driven noise is not observed, how do we establish the model, right? This we have to know this, or we have to assume some say if we don't have observation, because that's how we parameterize the model. Yeah. Any more questions? So that's it. That's for the yeah.
Zongren, can I ask you two questions?
Yeah.
Firstly, can you go back to the illustration figure? Oh, this one. All right. Okay. So the input data is some snapshot from U, right? The control path is the solution U, right?
No, it can be anything. So in the neural cities, the control path is interpolation from observation from the sequential data. But I checked their codes. For at least for some experience, they didn't put all the experience online. For some experience, sorry, the control path is on the driven noise. So it's
okay.
Yeah, the input data they interpolate the driven noise to the control path, and they treat it as control path. And but it can be for control path can be the input data, the U, different observation of U. Yeah, it can be done either way. It's pretty flexible.
Okay. So the control path is either U or C, right?
Or could be both. Yeah.
Okay, and then the response path is it the solution to the SPD?
I think it's a ZT.
ZT.
This one. Yeah, it's ZT to the and then for some transformation, and they obtain the output, the solution.
Okay, got it. Okay, and then the second question is about the first method for training, first method for training the parameters, the Ferre. Yeah, right, this one. Okay, so so you said here the matrix, the A is a matrix, so
yeah,
A is linear.
Yeah, I saw their codes. I wondered how they didn't say anything about parameterizing A in the paper, so I checked go to their GitHub and check that they're actually initialize A with as a matrix.
Yeah, well, I'm just thinking how restricted it is if you have this A to be linear, because if A is linear, then E to the TA is the solution operator to a linear system, right? I think so.
Right. Yeah. They do the parameterization for this part in a easiest way.
Yeah, and then that means the Fourier transform satisfies a linear system, but I think it's pretty restricted. Well, I just wonder how about changing A to some nonlinear stuffs. Just some random thoughts. Okay.
Yeah. In practice, this can be done, of course, if you can find a way to parameterize general nonlinear function A. But I think this idea is valid.
Yeah.
So but for the whole framework, it could be linear. If it's linear, the expressivity of your model could be low compared to nonlinear parameterization way, but it's easier to compute maybe. It's more computationally tractable.
Yeah. Well, I'm thinking about the Laplace transform.
You mean replace the Fourier transform with the Laplace transform?
I mean, when G is Laplace, G or F, anyone, you know, you have a Laplace of U. If you have a Laplace U in the SPDE, then I don't know, when you take the Fourier transform.
I didn't really go deep into their codes. I don't know how they deal with. They use code. They borrow code from neural cities to do this part, and I didn't check the Fourier transformation, the details. But,
okay.
And those are just the parameterization methods. So you can we can do. There are many ways.
Yeah. Thank you.
No problem.
I think that Tinwei makes a very good point there, because when you make the assumption that you have this decomposition of the linear plus the nonlinear, and you get this expression for Z, right, which depends on the evolution of the linear part, then this approach will work well when the nonlinearity is mild, is not strong. But if it's strong, then if you try to do the second method that they use a fixed point argument, you will need a lot of iterations to converge. Because if the nonlinear part, for example, you try to apply to Navier-Stokes with high Reynolds number, right? It will not converge fast, this fixed point approach. Because the Picard iteration, it's based on a Picard iteration, and it needs a lot to go away from the linear solution to try to find the nonlinear one. So for the problems that they tried here, probably it was not highly nonlinear. I mean, the nonlinearity is there, but probably it is for a weak case. Weakly nonlinear problem.
Yeah, it could be a problem.
Also, they're solving it for short times in general, right?
Right.
Where the nonlinearity didn't have enough time to develop.
Yes. I don't know why they don't extend it to even longer. The longest time is 1. It could be 10. It could be more. So yeah. So
I invite the first author to come and talk to us. They're a good group from Imperial, I think, and Warwick and from England. So we'll see if he responds.
All right.
Thank you, Zongren. Do we have more questions for Zongren? If there are no questions, we can end the session today here. And for everyone, have a great weekend and stay safe.